If the doubling period of a bacterial population is 20 minutes, and at time t equals 80 minutes, the bacterial population was 50,000, what's the initial population at time t equals 0, and what would be the size of the population after 4 hours? So we'll look at a strategy that works here. It would also work if we're working with half-life instead. And so if you want to know an initial population, the first thing that I'm going to figure out is my growth factor, or my value of b. So I'm thinking about my function f of t equals ab to the power of t. So because we're dealing with a doubling problem, I'm going to look at when is 2a equal ab to the power of how long does it take to double? In this case, 20 minutes. If this was a half-life problem instead of a doubling problem, instead of 2a, you would just write 1/2 a. So dividing both sides by a, I get that 2 is equal to b to the 20th power. So to solve for b, I'm going to take the 20th root of 2, but you could also think of this as 2 to the 1/20th power. So if you looked at some of the videos in the homework, a lot of times that's the way he wrote it, as a base of 2 with a power of 1 over the doubling time, or if it's a half-life, a base of 1/2 to the power of 1 over the half-life. So now coming back to the initial population, now we know b, we can use that given information about time t equals 80 in order to solve for a. So I'm going to say that f of 80 is our input, our time, is equal to a, the thing that I don't know, times t to the 1/20th power to the power of t, because remember we're thinking about the format a times b to the power of t. So the b is what we just calculated, t, the thing we're plugging in this time, is 80, and after 80 minutes we're told that the population would be 50,000. So I have a times 2 to the power of, when you have a power raised to another power, you can multiply those exponents together. So 1/20th times 80, you could think of that as 80 over 20. Or we know 80 over 20, we could go ahead and simplify that to 2 to the 4th, or 16a is equal to 50,000. But that setup is always going to work out being the same, that you'll have this fractional exponent where the denominator is your doubling time or your half-life, depending which type you're working with, and then the numerator is whatever value we're plugging in. So if we divide both sides by 16, we get that a is equal to 3,125. So this is our initial population. Once you know that initial population, we now know A and B, we can answer any kind of question. So given an amount of time, we can find the population, or given the population, we can solve for an amount of time. So the first step is always figuring out A and B in each of these problems. Once you have that, you can answer any number of questions from there. So we're asked about 4 hours. I'm going to think about that as 4 times 60, or 240 minutes. Since we're working with a unit of minutes, we need to stay with minutes as well. So f of 240, now we'll take that 3125 times our base of 2 to the 1/10th to the power of 240. So by using 2 to the 1/20th, I'm using an exact value for b, and then I can do just any rounding as needed at the end. In this case, we'll come up with a nice whole number. So we'd end up with 12,800,000 as we put that into our calculator. You can simplify those exponents first if you want to. Multiply them 1/10 times 240, or put that all in your calculator at once. This is a population, so this is telling us how many bacteria that we have after that time frame of 4 hours. So anytime you're working with a doubling period, you can start by figuring out what that base b is going to be by setting your function equal to 2a and using your doubling time in the exponent. Once you know your base of b, then we can use that given point to figure out our initial value.